Welcome to the channel. In the last video, my homemade GoTo mount worked great, but how did it get so accurate? In this video, I'll share the secret, the entire setup process, from building the mount to fine-tuning the Onstep firmware. Let's get to it. Since my planetary GoTo mount worked perfectly, I thought I'd share some info about its settings and how to properly set the planetary gear reduction ratios in the Onstep firmware. The mount I showed you in the last video is a mechanism that connects 4 planetary gears on a single axis. When the 4 gears drive each other, the gear ratio per axis is 410:1. I figured this out based on commercially sold mounts, and it turned out to be the best option for the gear teeth count, the physical size of the whole mount, and the 3D printing process that affects all of this. The structure is mainly made of PLA plastic. I know it's one of the weaker options, but when I started this project, I wasn't sure I'd succeed. After printing a few test models, I found it to be pretty solid. Plus, it's relatively cheap and easy to print. As for the gears, there are 3 in each stage, with herringbone teeth. This gear profile minimizes backlash and adds strength to the mechanism, making it better at transferring torque. The key to its smooth operation was filling the axes with a large amount of graphite grease. The mount uses Nema 17 stepper motors from an old 3D printer and an MKS GEN LV 1.0 mainboard. The Onstep docs warn you not to use this board, but you have to work with what you have. Downloading the firmware is simple. You can get it right from the Onstep project's GitHub page. Setting it up can seem a bit complicated at first, but once you open the firmware in Arduino IDE, you'll find detailed explanations for each parameter and value in the config.h file. There are also links to more detailed online guides. So, once you understand the basic logic, you can easily customize it for your specific hardware. The developers even made an Excel spreadsheet with functions, so you can just enter your stepper motor parameters and the physical gear ratios of your mount. It calculates the specific firmware values you need to change in the code to make your mount work right. In the Onstep configuration calculator, you enter your values in the green cells. The orange cells show the calculated results. For the Stepper Steps section, you enter how many full steps the stepper motor takes for 1 revolution. You can easily find this number based on your motor's type and part number. Next are the Axis 1 and 2 driver microsteps fields. This value is determined by the driver that controls and powers your stepper motor. In my case, it was the A4988, which is also not recommended, but it worked for me. The maximum microstep setting allowed by the firmware was 16, but other more advanced drivers allow for finer adjustments. The Onstep guides cover these alternatives in detail. For the gear reduction section, you need to say what type of drive you have, meaning if there's another gear system besides the main mechanism, and what its ratio is. Since I don't have a separate gear system driving the first stage of the planetary gear axis, I entered 1 in the GR1 Other Stages section. For GR2 Final Stage, I entered the planetary gears ratio per axis, 410 for both the axis 1, right ascension, and the declination axis. After that, you just transfer the values from the orange cells to the corresponding lines in the firmware code, replacing the default values. I left the slew rate based desired option at its default value of 1. During my first tests, I strangely noticed that the declination always turned in the opposite direction from the target in the sky. The time, location, and date were all correct, so I had no idea what the problem was. It was really starting to get on my nerves. The fix was to change the code line that controls the axis rotation direction in the Axis 2 settings, so the stepper motor would turn backward. You don't need a counterweight for a few reasons. First, the mount's planetary gear design provides high torque. Second, the two axes are as close to each other as possible, so the declination doesn't sit too high above the right ascension, adding stability. Also, because it's 3D printed, the structure can't move more than 5 kilograms. So if you put a telescope that weighs under 5 kilograms on it, like the Skywatcher EvoGuide 50ED, it can move it with perfect precision. Just out of curiosity, I tried it with my Skywatcher 150 PDS, a 15-centimeter Newtonian scope that weighs well over 6 kilograms with all its gear. When it moved the right ascension axis down by 60 degrees, it couldn't lift the telescope back up without help. I had to support its weight by hand, or the whole thing would have been destroyed. A question you might have is why it doesn't have a clutch like commercially sold equatorial mounts to let the axes move freely. The planetary gear design doesn't allow for free axis movement, and I didn't want to complicate the mechanism by adding a clutch. To get around this and make it easier to connect the two axes, I used tube rings with a rail and a slot at the end of each axis to hold the rail. This is like how most factory mounts use a dovetail bar to connect to the telescope. If I loosen the tube rings, I can turn either axis wherever I want. A few marks with a marker show where they were originally, so I found a simple but great solution to this problem. Some might think it looks a bit crude, but it works. Source of time and location. These data are critical for the GoTo function to work and for the mount to point to the right target in the sky. I did try using a GPS module, but even outside it had trouble. While it perfectly determined the exact location and date, it couldn't get the time right. The controller's clock was always off. But I didn't give up. I remembered that with my factory Skywatcher EQ5 GoTo mount, I never bothered with these things. I just used an EQ Direct cable to connect the motor controller to an ASI Air Mini astrophotography controller. The GoTo always pointed accurately to the target by relying on the ASI Air's calculations. So, with my mount, the ASI Air provides the time, date, and exact location to the Onstep. However, there was another problem. I didn't trust a used old 3D printer mainboard, power supply, and so on, so I added a USB isolator between them. This creates a fast connection without the two sides the ASI Air and the Onstep controller being physically connected. This way, even if the Onstep firmware board fries, the ASI Air remains safe. Safety first, right? Overall, this could be a homemade alternative to commercial models like the Skywatcher Star Adventurer GTI. Of course, the factory mount will be better in many ways, that's not even a question. But this project was so exciting for me. Every problem I solved brought up a new one. And as cliché as it sounds, the closer I got to the end, the more confident I became that I would create something truly amazing for myself. Something that is not only functional, but also looks good. If you want to see the results of using a DIY mount like this and the quality of images you can take with it, subscribe and like this video. You can also share it with anyone interested in building an Onstep controlled GoTo mount. Until the next video, may the tracking be with you.